International Journal of Computational System Engineering, member in editorial boards of several national and international journals, and is evaluator expert for national and international projects and PhD thesis. Dr. BALAS is the Director of Intelligent System Research Center. Ma'am served as General Chair of the International Workshop Soft Computing and Applications in 9 editions of the Inter and held in Hungary. Dr. BALAS participated in many international conferences as organizer, honorary chair, Session-2, member in steering, advisory or international program committee, and keynote speaker. Recently, she was working in a national project with EU funding support. Member of Society for Logic and Technology, member of Society for Industrial Applied Mathematics, and a senior member IEEE, member in Technical Committee. Ma'am was past Vice President of International Fuzzy System Association Council. Sorry. Ma'am is a Joint Secretary of Governing Council of Forum for Interdisciplinary Mathematics, a multidisciplinary academic body, India. And she awarded a prize from the Romanian Academy for the contribution in the field of soft computing methods. Now I request the host, Dr. Satvi Singh sir, to welcome ma'am.
Hello. Am I audible?
Yes, sir, you are audible.
Yes, I heartily welcome Madam Valentina, and she has joined us very timely because she has some other lecture in Jaipur from 1 to 2. Therefore, you start the lecture. Please, Professor Valentina. Hello. Professor Valentina.
Can you hear me?
Yeah. You are audible, ma'am. You please start your lecture.
And you can see also my screen, yes?
Yes. It is visible, madam.
Good. Just a moment. Magnify. Oh, it seems I cannot do just a little bit. I will stop and I will start again my presentation because something is not working. Let's see.
Madam, no issues. You please rejoin. Your screen is visible, madam.
It's visible, but it's a message here starting your meeting and it's in front of my screen.
Okay.
It's visible now, yes?
Yes, it is visible, madam. You can continue, please.
Mom, it is visible.
So first of all, I would like to express my appreciation to the organizing committee for inviting me in this important international webinar organized by you. And I can tell you that I visited Chandigarh. It's a wonderful city in 2018. going to another conference in Punjab. I really appreciate all that you are doing there, and especially people that are very smart and working so hard. My presentation, it's a long one. Maybe I will skip some slides. It's about some applications in this field of intelligent optimization control methods. And few words about this William of Ockham. He said at the moment that entities are not to be multiplied beyond necessity. So things are very simple, and starting from simple things, we can arrive to more complicated, but it's not necessary to complicate too much. You will see some very easy to write formulas that we introduce in our research, and that is working so nice. So this was a philosopher and also working in mathematics. I will skip, as I told you. So we were interested also in intelligent circuits because using such intelligent circuits, we organize our practical applications. You will see that we introduce a family of controllers, fuzzy interpolative controllers, and we were very much concerned about how to organize in a physical way such circuit. And we proposed to some producers of such devices to produce as an ASIC circuit, but they were not interested. And at that moment, we found, our team found very easy the solution. We implemented in FPGA, and everything was very nice. So we will try to see such controller that we will introduce. And as application, you will see self-adaptive control. And also in few words, I will tell you something about commuting effects, switching controllers, instability. So here's the content. And also in the side of introduction, I will tell you about Catherine Lualdi. So she wrote this book, Sources of the Making of the West, in this volume 1. She said the next sentences: the study of science varied widely from Greek to Roman society. The Greeks studied theoretical sciences and mathematics, among other things, writing theorem and proof for mathematical laws. It is clear from Archimedes' letters to Eratosthenes at Alexandria that Greeks valued knowledge for its own sake beyond just its practical applications. But Romans research focused primarily on practical applications. They excelled in the science of engineering, in architecture, and so on. So you can see Greek and Roman. Our roots, Romanian, are Romans. We are a Latin language, but the influence of Greeks was also in our region. It is well known that people are using instinctively linear interpolation as a basic learning technique. And also comparing interpolative networks to neural networks, we can see that interpolative networks are not suited for automatic learning, neural networks are suited for automatic learning, and interpolative networks are capable to embed and process knowledge. This is very important for us. And the starting point for fuzzy interpolative systems that are used in our control side started with interpolative networks from Sir Isaac Newton as universal approximators, but also the roots are from fuzzy logic developed by Professor Zadek. It's about knowledge linguistic representation. Our approach, fuzzy interpolative methodology, show us a fuzzy interpolative controller that is a controller that can be equaled with an interpolative network that I have introduced before. So there are fuzzy control rules that have each one a corresponding interpolation node, and very easy, the immediate result, it's that can be implemented by lookup tables or other similar tools, even in analog integrated circuit. A derived concept is fuzzy interpolative expert system. And in few words, I will develop this fuzzy interpolative methodology. We use in developing this methodology 3 different sources. First, it was about the papers of Zadek, Sugeno, Bauer, and you can see here the Sugeno fuzzy controllers. They can approximate finite n-dimensional function with arbitrary precision. You can see the red line is an approximation for the black line. Then papers of Stoll with linguistic design methods, and last, Cloxin, Morgan, and Laurent Foulois. It's about qualitative control based on the real-time online qualitative analysis of the error phase trajectory. With Professor Laurent Foulois, I spent 2 months in France during my PhD documentation, and they are working, their team in Annecy. They are working with such qualitative control methods. Also, the main model, it's very easy to understand, starting from controller with immediate linear interpolative equivalent. We are using fuzzy triangular partitions, prod sum inference, and center of gravity defuzzification. Here is Professor Sugeno, visited my country every 2 years for my conferences that I'm organizing here, soft computing and applications, and he is the honorary chair of my conferences. In the same time, Professor Zadek visited Romania 5 times to my invitation, again in my conferences or in other occasions. In closed-loop control application, fuzzy interpolative controllers are matching this fundamental time analyze tool, the phase trajectory of the error, that is associated with qualitative analyze. Here it's very easy to understand the methodology. First, we are using the phase trajectory of the error. You can see the error and the derivative of the error. And this trajectory that is going to 0. This is our dream. People working in automation, the error to be 0. Then we are speaking about McVicar-Velan tables and the interpolative networks implemented by lookup tables. Very easy. Anyway, to understand very well all that is here, this methodology, the classical automatics must be very known. And after that, the information is so much concentrated here. So it's not so easy to understand at the first sight. So this fuzzy interpolative methodology is taking from these 2 linguistic and interpolative nature of fuzzy systems. You can see A and B, fuzzy set and logic during construction development, and linear interpolation during implementation. Fuzzy development, interpolation, implementation. There are some basic steps. I will not insist on them. You can see for these 2 points, for A and B, how we are organizing and developing our systems. And also, such controllers are standing for the best control solution only if we provide them with relevant knowledge about specific control process. This kind of knowledge, Professor Zadek named world knowledge. And we can introduce them in these lookup tables. Here are the members of this family that we developed, our team developed during some years. Plane surface adaptive interpolative, fuzzy self-adaptive, and fusion fuzzy self-adaptive interpolative. Here is the plane control surface adaptive, and the structure of the first member of the family. It's in this figure, it's about 3D lookup table with the central point that is different, only central point. You can see -2, 0, +2. Because we are using the error, the derivative of the error, and the integral of the error. This qualitative analysis that we were inspired from France, from ANSSI. So integral when it's positive, 0, and negative. Here are some different control surfaces. During the conference of computing, World Conference on Soft Computing in 2018, we discussed a lot with Professor Jerry Mendel. You know that he introduced fuzzy type 2 systems and so on. And it was a very nice discussion with him. Then the next member of the family is organized around the first one, putting these blocks. And here it's a simulation just to show that this controller is working better than a PID1. You can see the step response here, the blue line that is going very fast to the value that we introduced, 1. So there are also some development of the control rule base to organize the corrector and so on. You can see here many things, but very important are these different categories, 4 categories or operating regimes: stationary, transitory, oscillatory, and unstable. And we are working, as I told you, using the phase trajectory of the error, qualitative analysis of the phase trajectory of the error. These are the 4 regimes, and what is happening with the gain in each regime. For G1, transitory, G2, steady, oscillating G3, and unstable G4. You can see this in this figure, this operating regime, G2, 3 oscillating, G4 unstable, looking in the plane phase error and the derivative of the error. Here is the heuristic adaptive rule based, organized again in this table, the error and the change of the error. And we are looking to the correction factor. Here it's how to implement in lookup table everything. And here it's a possibility to see how is working this controller comparing with the PID1 that has big oscillations. A fuzzy self-adaptive interpolative has small oscillations. This is the last member of the family, is organized using the first member and then putting other blocks. And here is the step response for this kind of controller. We can see that the response is good for simple systems, but for systems like third order system with the dead time, there are some oscillations. So there are some benchmark studies that confirm this remarkable potential of fuzzy self-adaptive interpolative controllers. And it's important that we are using first of all in two applications, because we working, me and my husband, the principal person in this team, together with our colleagues and PhD students, we were working for 9 years in an institute for research in railway coaches. It's the biggest factory for railway coaches in Southeast in our city. And the first applications were this air conditioning equipment using this controller and an ABS braking. So we observed that they were working very, very well for this kind of highly nonlinear systems. This is about the air conditioning installation for uncompartmented passenger coach using this fuzzy self-adaptive interpolative without adaptation, and with adaptation you can see oscillation very, very small. It's an ABS controller. I will come back to this. And again, some simulations by introduction of adherence perturbation, different oscillations, and some advantages of such controllers. It's very easy and fast to develop them. And as I told, after developing as lookup tables implementation, it's very easy using FPGA. They have good performance and cope with unknown process, and also they are efficient implementation in any of software and hardware non-technologies. Here also I will introduce, I want to arrive to that side where I am discussing about optimization. So another interesting chapter that we studied in our last years were related to what is happening when we switch for a controller to another one. More precisely, how what is happening when we switch from manual to automatic pilot, let's say. So we know that we are dealing with digital systems, and the fundamental advantage of such digital systems are very well known, and still they have limitation. Why there are limitations? Because it's an oscillatory behavior caused by the discrete action of an ABS controller. You can see in this figure such a system, what is happening when we want to produce a braking for a railway coach, because it's the figure from there. So we have this line, upper side, it's the speed of the railway coach, and this blue line down, it's the speed that we collect from the wheel. So these two speeds are not the same, because sometimes the wheels are sliding over the rail, and the braking force is working like this. So it's a digital system. You can see a lot of oscillations. Switching controllers instability, because it's an important chapter here to discuss. We need only to think to the phenomenon nuclear plants to Chernobyl. There it was happening, this phenomenon. So they try to switch from automat to manual mode, and it happens this big error there and a big accident. The same things are happening also for airplanes when they want to switch from pilot, automatic pilot to manual pilot. Why? Because algorithms need either a perfect state initialization of the switching action or a certain time computing cycles to take over the control process. So there are some processes that are happening there. Some detailed studies of switching phenomena were reported, but mostly for linear systems. Switching systems can be potentially destabilized by an unlucky choice of the switching moment. For Hurwitz stable closed-loop systems, this stands even for identical switch systems. Even they are identically, you will see in some simulations what is happening there. The concrete implementation of the computer that performs the simulation process control can produce the same effect, integration method and tuning, sampling rate, and so on. So the frequency analysis cannot be used because transfer functions are defined for null initial conditions. So for nonlinear systems, the frequency analysis has chances to produce results because the lack of unified theory. A better solution, the time analysis. So we can use again this phase trajectory that can fully support the design of switching controllers for linear systems. And we aim to move these techniques toward nonlinear, replacing the precise control of the phase trajectory that can be achieved in linear systems by qualitative analysis of the phase trajectory. As I told you, related to the work of Professor Laurent Foulois. The method can be easy again implemented by fuzz interpolative. A benchmark study, we have a PI and a PD controller, and we want to switch controller for a DC drive. There are some real data here, and we have for PI controller and for PD controller. And in this figure, you can see it's written PID to both, but one it's PI, one it's PD. And we want to switch from one to the other one. We have saturation and we have here the DC drive. And we will take a look what is happening when we are doing this switching action. And we introduce some different time when the switching moment will arrive, and just see to see here what is happening. So from some real data, we put here what is happening with the PI controller. PI controller, it's keeping 6 rotation per minute. And at the switching moment, in this moment, switching from PI to PD, we can see that the value is going up instead to maintain it. So it's an instability just when you switch from a controller to another one. This slope can be also negative, can be positive, going up or going down. So if we try to switch, you can see at 5 seconds, the slope is going down. If it's at 4 seconds, slope is going up. When we switch from one to the other one, the output of the two controllers in the moment of commutation at 3 seconds. At 3 seconds, we can see what is happening. So there are some empirical observation. So controller instability may evolve in both senses, positive and negative. It can appear as well as in the case of same type controllers. We can have PD, and is happening the same. It is finally producing the saturation of the controller, but its causes are not necessarily linked to the saturation. And it is essentially depending of the simulation's parameters, integration method, error, and even the simulation hardware. Switching control instability is linked to oscillatory responses. Here are some images, what is happening, thinking that we are working with digital systems, like in optics, when it's appearing the aliasing effect caused by the digital systems. A visual effect here in this figure. So such possibilities can appear, and it happens to Chernobyl. Again, we introduce the qualitative analysis of the phase trajectory of switching error. So we are looking now to the error of a PI and a PD, which is the error, and the corresponding will be the phase trajectory of the switching error. Like here, this is the error and the derivative of the error. The blue line, the error, the derivative of the error. And we can obtain this figure here. What we can observe is that this point of commutation is not recommendable switching to have this switching in the first quadrant. So it's not recommended. Also in the third quadrant, not recommended. It's recommended in the second and the fourth quadrant. If we have in mind this criterion where to switch, we can choose the switching moment, the risk of producing instability decrease massively. So in fact, we never assist such case, but this is not demonstrated. So empirical observation, a particular high risk zone, we observe this. And looking to this figure, we are inspired by sliding mode control. And again, sliding contour is happening in the second and the fourth quadrant, not in the third and first one. Some few applications, they are related with this airplane, here Jet 25. We have here the model, the pitch angle to elevator transfer function, and it's a third order system. And again, we have two controllers. We want to switch from one to the other one and to see how is going things there. So a correct pitch angle step response for PD to PI switching. So from PD to PI, there are some oscillations, but maintaining. But if we are switching at 2 seconds, let's see here in the interval 0.5, you can see that the output is going up or going down. If you are going to switch to 4.5 seconds, the results are okay. Again, here we have an instability. For the other airplane, we have only few oscillations. You can see here. So the results are more working better. Some recommendations, what can we do in this case? So in this case, replacing the digital systems with analog circuitry, this is an extreme measure and is causing interface complication. A better version of this idea is to remove the feature that can cause instability for switching control systems. I will go further. So Nyquist-Shannon sampling theory we are using again this. Why? Because it's perfect for information transmission if we know the channel bandwidth. If not, one measure it in 3 minutes, largely used in automated control too. Still, in case of complicated plant, highly nonlinear, like an airplane, who really can know the bandwidth? Here, B, it's that idea excluding the switching moment when they are located in the first and third quadrant. And here, it's a solution for this problem. So we have the active controller, we have the unconnected controller that want to switch after some time, and the process. And what we are doing, we are introducing for the second controller the same conditions, and we try to see when the output is the same, exactly the moment to switch. There are some simulations, and we can see that in this case, we find the solution and the output is okay. Now some applications. I will introduce you. Railway coach air conditioning. Compartmented railway coach, and we are trying to maintain the temperature, and even the system is a dead time system, highly nonlinear. We can control with some small oscillations, you can see in this figure. So we had the real railway coach, and we simulate them in MATLAB Simulink. You can see here the whole railway coach and the system too. Here it's related to intelligent transportation, other applications for an ABS braking for railway coach. We have here another application, imposed brake distance. Imposed brake distance means to create such a mapping, position, velocity, like in this figure, and using the computer model to decide if this railway coach is stopping in an imposed brake distance. This is very important for railway equipment, because if locomotives are not stopping in a certain distance, they have some problems with their wheels because of braking force, and the distance to stop is too long, and they are not able to circulate. They are turned. Now here is what I want to introduce you, the optimization of the distance between cars. So we have a lot of systems like this one, the adaptive cruise control, and the other systems that are very much introduced nowadays, because we are looking for the autonomous car, you know very well. And in this side of the lecture, I will present you a new optimization method for highway traffic. So as I told you, for intelligent transportation systems, there are many systems like advanced driver assistance systems, when designed with the safe human-machine interface, and it should increase car safety and road safety. Again, adaptive cruise control, intelligent cruise control, everything just to avoid collision in such a system organized not by two cars, but many cars. So some of the dangers that sensors that are introduced in such systems can pick up on include how close the car is to other cars surrounding it. like here in these following cars on highway. Such intelligent speed adaptation or intelligent speed advice are systems that are constantly monitoring local speed limit, the vehicle speed. And we have also in-vehicle navigation systems like GPS or traffic message channel. We have lane road departure detection, lane change assistance, night vision, and so on. Other facilities that we are studying, you know, very well, pedestrian protection, automatic parking, traffic sign, and so on. So such a systems is introduced in this figure. Nowadays, our cars are very intelligent and have a lot of systems there. And even Professor Zadek said that the most complicated task is to have a parking of a car. Nowadays, you can commute on automat and you can have parking automatically. So automat driving is likely to produce at its turn safety risk by the driver distraction and reduce situation awareness, causing in time the reducing of the driving skill. There are different facilities, human-machine interface. You can see there are a lot of information on the screen for the cars. Some traffic indicators now. In the car following algorithms, there are some indicators introduced just to measure the characteristic of the traffic flow. Time to collision, the time to accident, post deceleration to safety times, and so on. But this is the criterion that we are working on it, and we observe that it's very useful for many students and for many people working in industry. The time to collision criterion. It's so easy. I started the presentation with that sentence that we do not need to complicate things. Things are very simple. So this formula, time to collision, means the time that it takes before car 2 collide with car 1, assuming unchanged speed of both vehicles. And that formula, it's there. Negative time to collision implies the car 1 drives faster, and it's no danger, but positive time to collision express an unsafe approach, and the situation imposed to do something. But because in that formula, if the denominator is 0 when the speed are equal, and we will obtain plus minus infinite, time to collision is replaced with inverse time to collision. And you can see the same formula, but inverse. Some simulation scenarios are here. I from draw to another one, and I lost some data here, but you can see only the relation between speeds. And here is the diagram, the distance between cars and the difference between speed. And the evolution of the time to collision and of the inverse time to collision in this figure. We are using such diagrams, inverse time to collision, trajectory, and the corresponding fuzzy partition assisting the driver. So using a fuzzy set that we introduce here, and we need some region, we do not need a certain data. And in this blue region, no risk at all. In this green region, we will preserve the trend and then easy braking. And in this region, it compulsory Using such criterion, we can optimize the distance between cars. In literature, we discovered this law in Formula 3 that it's very strange because there are some coefficients that has no meaning for humans. So we compare our constant time to collision criterion with this formula introduced. And you will see after using our criterion, we can see if the speed is 200 kilometers per hour and the time to collision it's 4 seconds, which is the distance between cars. The distance is bigger and so on. We made the simulations with 2 cars going in tandem and just to see how they can preserve the distance between them and be a safe driving. Here is the polynomial that is with no meaning, and you can see that it's going up and it's hard to interpret. But applying this criterion, a constant collision risk for each vehicle and the possibility to control the traffic flow on extended road sectors. Again, we are using such fuzzy interpolative distance controller. This is the control rule of the distance controller, introduced very easy. This is the PD fuzzy interpolative rules control. And it's interesting that we can use it to maintain distance between cars, different simulations. So we can have a traffic management using this criteria. And also it's interesting to develop for constant time to collision platoons idea. Now we will have a platoon, not only 2 cars. And we put here 5 cars, you can see, and each one is following the other one. And how is organizing in a platoon? In few seconds, they are organizing in a platoon. First, their speed is varying. Here you can see 5 cars, they are going in a platoon and maintaining the distance between them. The same, so this criteria is an optimization criterion that is in the case of 2 following cars, and that is imposing a distance between them. I think I will stop here. I have also I will pass through other applications, greenhouse intelligent control. We have also optimization here, how to maintain the temperature inside using the same techniques. What is happening, we are decreasing the consumed energy. And also, I forgot to tell you that in this constant time to collision criterion, we can obtain economy in fuel gas, and the Renault company used criterion and they obtain 25% fuel gas economy. And different oscillations and conclusions. So this family of fuzzy interpolative can help us in optimizing our systems, optimizing a lot of, first of all, controlling, helping to control them and optimize their function. Thank you very much for your attention. There are
Thank you,
questions.
ma'am. Thanks a lot, ma'am, that you have spared your valuable time for this international webinar. Thank you. Now it's time to take the queries from the participants for Professor Valentina Balas, ma'am. And for this, I request the host to allow the participants. If you have any queries, you can write it in chat box or you can mute yourself. You can unmute yourself. Yes, any queries from the participants? Any queries?
Sir, I am Dr. Meherchand from India. Yes,
Yes,
we
sir.
know there are a lot of
Yes.
applications in control theory, and also we can use optimization techniques. But I think optimization technique not appears in the form of fractional order. So can how we can apply both together to make a intelligent machine? So this is the problem from my side.
Yes, just now we are working on fractional order systems with my PhD student, Tanya, developing such a control uh, law for artificial pancreas. So for sure, the results will be very good. I know because I had also in some applications fractional order systems together with fuzzy control. If you try to find in my papers some years ago, I had this kind of direction. But now I came back because Professor Dumitru Băleanu is also with us and he's helping a lot. And I'm happy to see you here, Mehar. And I'm sorry you cannot come in Romania in 2016, I think, or 18, but I hope next time to be with us and to develop some nice applications. Thank you.
Thank you, Professor. Thank you.
Thank you, ma'am. Thank you. And any other queries from the participant, they can write it in chat box also, if you have any queries. We are just getting here. Thank you, ma'am, for the excellent and impressive representation. Ma'am, maybe there will be no queries for the session. Thank you, ma'am. Thanks a lot. Now I request Dr. Satyavir Singh, sir, convener of this webinar, to thank ma'am and to present the certificate of appreciation to Dr. Balas. Thank you.
Professor Stabir, please unmute. You are muted.
Hello. Madam, we feel honored to see you and listen you in Punjabi University Patiala. But when pandemic issues are over, we will love to invite you in Punjabi University Patiala physically. And we will also love to collaborate in research with you. Thank you very much for thought-provoking lecture and guidance. Thank you, madam.
Thank you, sir. Sir, please give
Thank
the
you,
appreciation, present the appreciation letter to ma'am. Certificate of appreciation for ma'am, please. Yes, I want the host to present the certificate of appreciation. Thank you, sir. Now I request all the participants to join the next session after half an hour. Thank you for this session. Thank you all.
Thank you, sir.